Today we're going to cover the 5.2, the derivative function notes. So students will be able to find the derivative using what's called the power rule. So average rate of change, I want you to think about, is slope. Slope is an average rate of change where you do y2 minus y1 over x2 minus x1. So and I'm not sure why it did this, but having some trouble with my math symbols. I might have to play around with it a little bit more, but delta y stands for the change in y. Okay, the delta symbol, it's a Greek symbol. So the change in y over the change of x is the average rate of change. Well, f of x sub 2 is y2, and f of x sub 1 is y1. So in other words, if it's a line, the average rate of change is the slope. So you will see that right here. If a function is linear, the gradient or slope between any 2 points is the same. And hence, the rate of change of the function is always constant. And that's true for a linear function. This, however, is not the case for nonlinear functions. In order to explore the gradient or rate of change of a nonlinear function, you first need to learn some essential definitions. Back from geometry, you had something called a secant line. So let me just use my little highlighter here. Do you see that? The little red flashing. There's your secant line. And a secant line is a line that intersects 2 points of a curve. So the green is a secant line. A tangent to a curve is at a specific point. It just touches the curve at 1 point. So I'm going to actually, let's get some letters on here. Let's call this A, we'll call this B. So line AB is a secant line. And let me change colors here. And then let's say line CD is a tangent line. All right, so now in the second diagram, now the green line is a tangent line. Okay, so let me maybe call this point A, and we'll make another point down here. We'll call it point B. And so here, line AB is a tangent line to the curve at point A, okay? So now, it's also a secant line. If I made another point somewhere on the purple curve, I could make a secant line in there, but for what I'm referring to, the green line is a tangent line at point A. The gradient, or slope, of a second line AB is f of x plus h minus f of x over h. Does that look familiar? Okay, let me kind of draw something here for you, okay? If I had a point xy and a second point that would be a distance of h apart, okay? Then this would be f of x plus h. And let me go back here. Let me see if I can't erase that here. Let's call this x f of x, okay? So say I have a point xy, or we're going to call it x f of x, and then say I just scooch a teeny tiny distance away of h. So now I'm, instead of saying I'm at point 1, now I'm at point 2. So I went 1 unit over. Okay, so then the slope would be y2 minus y1 over x2 minus x1. Well, then what ends up happening is the x's cancel. And so this is leading me somewhere, okay? This is really leading me to something in calculus. We're laying a foundation here. So this is also called the difference quotient. But this gradient or slope is the average rate of change of f of x between x and x plus h. As point B gets closer and closer to point A, the gradient of AB approaches the gradient of the tangent line to the curve at A. So the gradient of the tangent line to the curve at A is the value of the limit, and I'm going to write it this way. So we've been talking about limits. So this now becomes the limit as h approaches 0 of that rate of change. So what's super cool is we can actually get h to get closer and closer and closer to 0 in the limit. All right, so the gradient or slope of the tangent line to the curve at A is the instantaneous rate of change of f of x at A. This instantaneous rate of change is called the derivative of f with respect to x. So we use f, and the way that you're going to read this is f prime of x. Okay, so let me say this. The way that you read it is f prime of x. That's how you say it. F prime of x or dy dx. Again, the slope of the tangent line to the curve at point A is the derivative at A. Let's maybe write that down, okay? That's important, okay? So, the slope or gradient of the tangent line to the curve at point A is equal to the derivative at point A. Okay, this is going to be really, really important. Okay, the slope of the tangent line to the curve at point A is equivalent to the derivative at A. It is also the instantaneous rate of change. And we use this new notation, f prime of x or dy dx. So let's take a look at example 1. It says, a particle moves in a straight line so that its position from its starting point at any given time t in seconds is given by s equals 3t squared, where s is in meters. The particle passes through a certain point when time t equals a, and then sometimes later through another point when t equals a plus h. So A says find the average speed of the particle from t equals a to t equals a plus h. So the average speed is going to equal, and you're going to take, okay, this is like the first point. Okay, this is like your first point, and then this is the second point, okay? And then you're going to plug it in. So t is like my x value, and s is like the y value. So I'm going to do 3, so it's like y2. This is y2 minus y1 over x2 minus x1. This is what I'm doing. So it's 3 times the quantity, a plus h squared minus 3a squared. Again, that's y2 minus y1 over x2 is a plus h minus a. So now we're going to do some algebra. That's a squared plus 2ah plus h squared. So, and again, I'm assuming at this point we're good to go with our algebra. So the 3a squareds cancel. And then can we multitask here? Can you factor out, oh, I won't this first time. Okay, I'll pull out the h, and I'll have 6a plus 3h over h. You can cancel that. So that, I'll move it over here, is 6a plus 3h. So that's my average speed formula. Okay, that's the average speed. And I'm not quite sure why I have a graph there. Explain how you could find the speed of the particle at the instant t equals a and find the speed at this point. Okay, so here's the deal. The speed of the particle at t equals a is the gradient or slope of the tangent line to the curve at point P. This tangent line is found when h is 0. So if you let h be 0, that's 6a plus 3 times 0, so it's 6a. All right, so the instantaneous rate of change is the derivative, and the derivative ends up being the limit as h goes to 0 in the average rate of change formula, or the difference quotient. So the process of finding the derivative of a function is called differentiation. Differentiation. So the nice thing is, if that's a little confusing, we are going to circle back to that a little later, but especially in this chapter and in later chapters, this concept, but we're going to do some super simple things here. If you have a function f of x equals x, and x is the variable, to the n power, where n is a real number, then all you do, it's called the power rule. You just bring the power down and decrease the power by 1. So in example 2, if f of x is x to the 11, f prime of x, which is the derivative, you bring down the power and decrease the power by 1. That's it. That's the power rule. It's really simple. Now, in letter B, I don't have it right now as x to a power. So what you have to do before you do the power rule is you need to rewrite this so that it is in the form f of x equals x to the n. So let's put a little star here, is you do need to rewrite f of x in x to the n power before you actually do the derivative. So, and then you do f prime of x, I bring down the power, and now you're going to decrease it by 1. That's actually going to be a negative 5. So that's negative 4 over x to the 5th power. All right, so here's a few other things about derivatives. If f of x is a constant, then f prime of x is 1. Or excuse me, f prime of x is 0. And if you have f of x is mx plus c, then the derivative is just going to be m. And if you have a constant times a function, you can just make it the constant times the derivative of that function. If you have addition and subtraction, you can just do the derivative of their individual additions and subtractions. All right, so let's look at example 3. If f of x equals 3 over x to the 11, so the very first thing you have to do is you have to rewrite this so that it is in the power rule form. So you're going to rewrite this as f of x equals 3 times x to the negative 12 power. So the derivative is you bring down the power. So it's negative 12 times 3. And then if you decrease the power by 1, that's not negative 11. That's actually negative 13. So this is negative 36 over x to the 13th. Only negative exponents move down. All right, in letter B, right now you don't know of the quotient property or the quotient rule. There is one, but it doesn't work maybe the way that you think. So I do need to divide this out. So what I'm going to do is I'm going to take everything in the numerator and I'm going to divide it by x squared. So what I want you to see is I made that 2x to the 4th over x squared, that's 2x squared. I took minus 3x cubed over the x squared, that's minus 3x to the 1st. And then 1 over x squared is x to the negative 2. Now I can do the derivative, and that'll give me 4x minus 3. I bring down the power and decrease it by 1. So I'm going to tidy that up and make that 4x minus 3 minus 2 over x cubed. All right, so do you notice like I did addition and subtraction and I could individually compute the derivative as long as it was of the form f of x equals x to the n power. Okay, so how much can the cyclist on the right lean inwards in order to negotiate a bend without falling off? In order for a cyclist to move in a circular path, a certain force is required to keep him from shooting away from the circle at a tangent. This force is perpendicular to the tangent, to the curve of the circular path. So we have a definition, and it is the normal line is a point on a curve that is perpendicular to the curve's tangent at that point. So a lot of times I just think the normal line is really the perpendicular line, okay? So the normal line is just the perpendicular line. So if you look at example 4, it says find the gradient function of f of x equals x squared minus 4 over square root x. The gradient function is the slope, and the slope is the derivative of the tangent line, okay? So watch what you're going to do. I'm going to first rewrite it so that this is x squared minus 4x to the negative 1/2 power. Okay, so the square root of x is x to the 1/2. So let me just have you recall that. The square root of x is x to the 1/2. And then if it's in the denominator, it's just to the negative 1/2 power. So what it's asking me is to find, when it says find the gradient function, that's another way to say find the derivative, okay? So that'll be 2x. When I bring down the negative 1/2, that becomes plus 2, and then that's x to the negative 3/2 power. So if you need a little bit of help with that, let me do it off to the side here. You would decrease the power by 1, okay? Negative 1/2 minus 1, that's negative 1/2 minus 2/2, and that's where I'm getting the negative 3/2. So that would be 2x plus 2 over x to the 3/2 power. All right, so that is the gradient function. Okay, that is the gradient function. So you just got to get used to it. Gradient is slope, slope of the tangent line is derivative. All right, now it says find the gradient of the tangent to f of x at the point where x is 4. Oh, okay. So all that means is do f prime at 4. So that's 2 times 4 plus 2 over 4 to the 3/2 power. So you get 8 plus 2 over. Now let me do a quick refresher, okay? We did this in Algebra 2. The 3/2 power means the square root of 4 is 2, 2 cubed is 8. So that's 8 plus 1/4. And you can either write 8.25, or if you get a common denominator, that's 33/4. All right, so there was a lot of algebra review in there, okay? There was a lot of algebra review. So fractional exponents, negative exponents, subtracting fractions, and then doing a rational exponent like the 3/2 power. I will try to get some office hours going so you can get some extra help from me if you're struggling with some of this stuff that I'm bringing back saying, oh, you're supposed to know that. All right, recall for perpendicular lines with gradients M1 and M2, if they're perpendicular, then the product of the two slopes are -1. So if a tangent line has a gradient of M, then the gradient of the normal line would be -1 over M. It's the opposite reciprocal. So if you look at example 5, it says the function f of x equals 3x squared minus 2 is given. Find the derivative of the function at x equals 1. Well, the first thing we have to do is we have to find the derivative function. So that would be 6x. Then, if I want to find the derivative function at 1, that's just 6 times 1, which is 6. Now, you're going to see why I did that chapter review stuff with you now. I was trying to set you up for success. I wanted you to be able to do really well. It says, write the equation of the tangent to the curve at x is 1. If I want an equation, we're going to use what's called point-slope form. Point-slope form looks like this. Y minus y1 equals m times x minus x1. Well, you need a point, and here's where it's like inferred. If I come back up here and I plug in 1, 3 times 1 is 3, minus 2 is 1. So I actually have a point, even though they only gave me the x-coordinate. So then here's my equation. Y minus 1 equals 6 times the quantity x minus 1. That's it. You do not have to put them in y equals mx plus b form. Now, our slope, okay, remember the slope is the derivative. So our slope is 6. So if I want the equation of the normal line, I need a perpendicular slope. So that would be -1/6. So guess what? I already have the point 1, 1, and the only thing that's changing for the normal line is the slope. That is it. All right, so let's pause here a moment, make sure we're getting the hang of this. So the derivative of the function, you have to do f prime of x and just plug in 1. If you want to write an equation, you need a point and the slope. If they give you the x-coordinate and you have a function, you can find the y-coordinate to complete the point. So then you plug in the derivative is the slope. Okay, the derivative is the slope of the tangent line. And then normal just means perpendicular. All right, so then our last example says find the equation or equations of any horizontal tangents to this curve. Okay, now I want you to stop and think. What do you know about a horizontal line? And again, this is why I had this in that chapter 2 review. I was trying to help you. Horizontal lines have slope equal to 0, don't they? Let me say that again. Horizontal lines have slope equal to 0. So guess what we're going to do? Now, you can do dy dx. Okay, I know if you have f of x, we write the derivative as f prime of x. If you have y, you can write it one of two ways. You can write it dy dx, or you can do y prime. And you'll see me use either. Okay, if you're given f of x, the derivative is f prime of x. If you're given y, you can do dy dx or y prime. So let's go ahead and we'll do dy dx. So I do the power rule. I bring down the power, decrease the power by 1. Now, if I want to find the equation of the horizontal tangent lines, horizontal lines have a slope 0, so then the derivative is 0. So I'm going to factor out the 6. And I'm going to keep factoring. So the x coordinates would be -2 or 1. So then how would you find the horizontal tangent line? You just have to plug those numbers in to the equation to find the corresponding y values. So when I did that, for this first one, I got y was 21, and over here I got y was -6. So those are my horizontal tangent lines. Again, I just plugged in x was -2 in here, and then I plugged in x was 1 to get that. All right, that wraps up 5.2.